two particles are created in a lab. They've never met before this moment. They exist for less than a nanosecond in the same quantum state. Then they're separated. One travels to a detector in Geneva, the other goes to a facility 80 kilometers away. When you measure the first particle's spin up or down, the second particle, in that exact instant, adopts the opposite spin. Not after a signal crosses the distance, not through any known force, instantaneously. Einstein called this spooky action at a distance, and he hated it. He spent the last decades of his life trying to prove it couldn't be real, but every experiment we've run since has confirmed it. The connection exists, and no one knows how. This isn't about faster-than-light communication. It's not about telepathy or mysticism. It's about something stranger. The universe appears to allow correlations that shouldn't be possible if space and separation mean what we think they mean. And the more precisely we measure this phenomenon, the more undeniable it becomes. The technical term is quantum entanglement. You've probably heard of it. But the actual physics of what's happening, what it means for two particles to share a quantum state across arbitrary distances, remains one of the most uncomfortable facts in modern science. Not because it's poorly understood in a mathematical sense. We can predict entanglement with extraordinary precision. The discomfort comes from the fact that no interpretation of quantum mechanics can explain how this correlation persists without violating something we thought was fundamental about reality. Let's start with what entanglement actually is. When two particles interact in certain ways, they can become entangled. This means their quantum states are no longer independent. Measuring one particle gives you information about the other, no matter how far apart they are. In the language of quantum mechanics, they share a single wave function. They're not two separate systems anymore. They're one system spread across space. Here's a cleaner way to picture it. Imagine flipping two coins, but these coins are quantum. Before you look at either one, each coin exists in a superposition, both heads and tails at once. But these aren't independent coins. They're entangled. The rule is, if one shows heads, the other must show tails. Always. You don't know which is which until you check. But the moment you look at the first coin and see heads, the second coin, whether it's in the next room or on the other side of the galaxy, instantly becomes tails. That's entanglement. The outcomes are correlated perfectly, but neither coin had a predetermined value before you looked. That's the part that breaks classical intuition. In classical physics, correlation usually means hidden information. If you put a red ball in one box and a blue ball in another, then shuffle them and send one to Tokyo, you don't know which box has which ball. But when you open the box in Tokyo and find the red ball, you instantly know the other box contains the blue ball. That's not spooky. The information was always there. You just didn't know it yet. Quantum entanglement doesn't work that way. The particles don't carry hidden instructions. This was the heart of Einstein's objection. In 1935, he co-authored a paper with Boris Podolsky and Nathan Rosen, now called the EPR paradox, arguing that if quantum mechanics couldn't account for these correlations with local hidden variables, then the theory was incomplete. There had to be something we were missing, some deeper layer of reality that explained how the particles knew what to do. But in 1964, physicist John Bell proved that any theory relying on local hidden variables would produce correlations that obey a specific mathematical limit, now called Bell's inequality, and quantum mechanics predicts correlations that violate that limit. So if experiments showed violations, Einstein's hidden variables couldn't exist, at least not local ones. The experiment started in the 70s. John Clauser ran the first test in 1972. The results violated Bell's inequality. Quantum mechanics was right. Einstein's intuition was wrong. More experiments followed. Alain Aspect refined the tests in the 80s, closing loopholes. Anton Zeilinger pushed entanglement across longer distances. In 2022, all three shared the Nobel Prize in Physics for proving that entanglement is real, non-local, and not explicable by hidden variables. But proving something exists and understanding what it means are different problems. The Nobel recognized experimental confirmation. It didn't resolve the interpretational crisis. Because here's the issue: quantum mechanics doesn't explain how entanglement works. It only describes what happens. The math tells you the correlations will occur. It gives you probabilities, predictions, outcomes. But it doesn't tell you what mechanism connects the particles. It doesn't tell you how information about one measurement reaches the other particle. And critically, it tells you that no information actually travels between them, at least not in any way that could be used to send a signal. This is where the tension lives. The particles behave as if they're connected, but nothing crosses the space between them. No force, no field, no signal. Relativity forbids faster than light communication, and quantum mechanics respects that. You can't use entanglement to send a message. When you measure one particle, the outcome is random. You can't control it. So even though the second particle's state correlates perfectly, the randomness prevents you from encoding information. But correlation without connection feels impossible. If two things are genuinely separated, if there's empty space between them, how can they remain locked in perfect anti-correlation? How can the measurement of one instantly determine the state of the other without something passing between them? Some interpretations try to soften this. In the many worlds interpretation, for instance, measurement doesn't collapse the wave function. Instead, the universe splits. One branch has spin up here and spin down there. Another branch has the reverse. The correlation is explained by the branching structure, not by communication. But this trades one strangeness for another. You're now accepting the existence of countless parallel universes, just to avoid admitting that particles can affect each other across distance. Other interpretations, like pilot wave theory, do posit hidden variables, but not local ones. The wave function itself becomes a physical field guiding particles. Entanglement is explained by this guiding field, which is non-local by design. But that brings back the question, what is this field made of? How does it exist everywhere at once? And then there's the Copenhagen interpretation, which most textbooks still teach by default. It says the wave function is not a physical thing. It's just a tool for calculating probabilities. Measurement collapses the wave function, but don't ask what collapse means or how it happens. The math works. That's enough. Except it's not enough if you want to understand reality. If the wave function isn't physical, what is doing the collapsing? If it is physical, how does one measurement instantly affect a distant particle? Copenhagen dodges the question by treating it as meaningless. But the question persists. This is why entanglement remains uncomfortable. We have a phenomenon that's been experimentally verified thousands of times. We can create entangled particles on demand. We can maintain entanglement across 12,000 kilometers, as demonstrated by China's Jinan-1 satellite in 2025. We can entangle not just photons, but atoms, molecules, even macroscopic objects like tiny silicon beams barely visible to the naked eye. We've observed entanglement in top quarks, the heaviest known particles, produced at the Large Hadron Collider. We've even detected entanglement within protons, among the quarks and gluons that make them up. None of this should be possible if entanglement required a physical connection. The distances are too vast, the timescales too short, the particles too different. Yet the correlations hold, always. In 2017, researchers using the Mitzias satellite demonstrated entanglement over 1,200 kilometers, transmitting photons through Earth's atmosphere to ground stations in China. The experiment violated Bell's inequality under strict conditions that ruled out any subliminal communication. The correlations appeared faster than light could have crossed the distance. According to one study by Huan Yin and colleagues, the lower bound on the speed of these correlations is at least 10,000 times faster than light. But again, this doesn't mean information travels faster than light. It means the correlation is instant, but the randomness prevents signaling. And that's the paradox. The universe allows correlations that appear to transcend space, but it forbids using those correlations to transmit information. It's as if reality is designed to give us just enough weirdness to break our intuition, but not enough to break relativity. Some physicists have suggested that entanglement isn't really about particles influencing each other. Instead, it reveals that particles aren't truly separate. The entangled pair is a single system. Distance is an illusion we impose because we experience space as fundamental, but maybe space isn't fundamental. Maybe it's emergent, something that arises from deeper, non-spatial connections. In this view, entanglement isn't mysterious. It's what you'd expect if the particles were never really apart. This idea shows up in speculative theories like ER equals EPR, proposed by Juan Maldacena and Leonard Susskind. The idea is that every entangled pair might be connected by a microscopic wormhole, an Einstein-Rosen bridge. The particles appear separated in ordinary space, but they're directly connected through a hidden geometry. Entanglement and wormholes might be the same thing, viewed from different angles. It's a beautiful idea, but it's speculative. No one has detected a wormhole, and even if the math works, it doesn't fully resolve the interpretational problem. It just moves the mystery. Now you have to explain how wormholes can exist without violating causality, and why they only seem to appear for entangled particles. What we're left with is this: entanglement is real. It's been tested exhaustively. It's foundational to emerging technologies like quantum computing and quantum cryptography, but we don't know what it means. We don't know how reality accommodates correlations that seem to ignore distance. We don't know whether space is fundamental or emergent. We don't know whether particles are truly separate entities or manifestations of something more unified. And that's where things quietly become uncomfortable. Because the question isn't just about particles anymore. To understand why this discomfort runs so deep, it helps to return to where the problem first became impossible to ignore. Einstein thought he'd cornered quantum mechanics with a simple argument. If you entangle two particles and measure one, the other responds instantly, even across a galaxy. That seems impossible unless information travels faster than light, which relativity forbids. So Einstein concluded the particles must carry hidden instructions from the start, like two sealed envelopes containing matching lottery numbers. Open one, you know the other. No mystery, just coordination. But in 1964, physicist John Bell found a way to test this. He derived an inequality, a mathematical limit that any theory with hidden instructions must respect. When experiments finally ran in the 1970s and 80s, nature violated Bell's limit. Not slightly, clearly. The particles weren't following pre-written scripts. They were genuinely coordinating in real time, across distances where no signal could connect them. That result earned 3 physicists the Nobel Prize in 2022, not for discovering something new, but for confirming something deeply uncomfortable. The universe allows correlations that shouldn't exist under any local explanation. And that's where the unease begins, because we're not talking about a measurement error or a theoretical loophole. We're talking about a confirmed phenomenon that forces us to choose between locality, realism, or both. Let me clarify what's at stake. When 2 particles are entangled, measuring the spin of one immediately determines the spin of the other. Before measurement, neither particle has a definite state. They exist in superposition, simultaneously spin up and spin down. But the moment you measure one, both collapse into definite, correlated outcomes. If you measure spin up here, the other will be spin down there, always, instantly. Now, that sounds like communication, but it's not. You can't use entanglement to send a message, because you can't control what outcome you get. Each measurement is random. Only when you compare notes afterward do you see the correlation. So no information travels faster than light, which keeps relativity intact. But that doesn't resolve the deeper problem. It just relocates it. The problem is this: if the particles don't carry hidden instructions and no signal passes between them, how do they coordinate? One answer is that space isn't what it seems. Maybe distance is an illusion at the quantum level, and particles aren't truly separate. Another answer is that measurement itself isn't passive, that the act of observing one particle somehow reaches backward through the shared quantum state to affect the other. Neither answer is comfortable. Both suggest that the classical picture of reality, objects with definite properties existing independently in space, breaks down completely at the quantum scale. And this isn't speculation, it's been tested. In 2017, researchers entangled photons between a satellite and ground stations in China, maintaining correlation over 1,203 kilometers. In 2025, that distance extended to 12,900 kilometers between China and South Africa. The phenomenon scales. It survives interference, atmospheric turbulence, and the vacuum of space. What makes this stranger is that entanglement isn't fragile in the way you'd expect. It's been observed in top quarks at the Large Hadron Collider, particles so massive and short-lived they decay almost immediately. These quarks are produced at such high speeds that they fly apart faster than light could cross the gap between them. Yet their spins remain correlated. Measurement reveals entanglement persisting across distances where classical communication is provably impossible. And it's not limited to exotic particles. Researchers have entangled mechanical oscillators, tiny silicon beams about the size of a bacterium. They vibrate like guitar strings, and by carefully adding energy without revealing which beam received it, the team forced both beams into a shared quantum state. The energy boost was real, but which beam got it remained undefined until measurement collapsed the superposition. That's entanglement in an object you could theoretically see under a microscope. Even more unsettling, entanglement has been observed inside protons. Quarks and gluons within a single proton are entangled across distances smaller than 1/4,000,000th of a meter. These aren't separate particles floating in space. They're constituents of the same object, yet they exhibit the same non-local correlation as particles separated by continents. This suggests entanglement isn't something that happens between objects. It's something woven into the structure of matter itself. So why does any of this matter beyond physics? Because it challenges the assumption that the universe is made of distinct, independent parts. We think of objects as separate because we experience them that way, but quantum mechanics suggests that separateness is an approximation, a macroscopic illusion that breaks down when you look closely enough. At the fundamental level, particles that have interacted even once remain connected in a way that has no classical analogue. This is where the language starts to fail. We say particles are connected or correlated, but those words imply a mechanism, something linking them. Entanglement doesn't work that way. There's no signal, no field, no hidden thread. The correlation simply exists, built into the quantum state itself. And when you measure one particle, the entire shared state collapses, instantly affecting the other. But here's the twist. You can't tell from the perspective of the second particle that anything happened. Its measurement outcomes are still random. The correlation only appears when you compare results. So the second observer never experiences anything non-local. They just see random noise. Only when data is combined, always at subliminal speeds, does the pattern emerge. This is why entanglement doesn't violate relativity. No information moves faster than light. But it does violate something deeper, the intuition that objects have properties independent of observation, and that distant events can't influence each other instantaneously. Bell's theorem proved that you can't have both locality and realism. You have to give up one. Most physicists have quietly accepted giving up realism, the idea that particles have definite properties before measurement. This is the standard Copenhagen interpretation. Measurement doesn't reveal pre-existing properties, it creates them. The universe is fundamentally probabilistic, and outcomes are determined only when observation forces a choice. That keeps locality intact, but at the cost of accepting that reality is, in some sense, observer-dependent. Others have explored giving up locality instead. In Bohmian mechanics, particles do have definite positions at all times, but they're guided by a non-local pilot wave that connects them across space. This restores realism, but introduces instantaneous influences. The theory reproduces quantum predictions exactly, but most physicists find the non-locality too uncomfortable to adopt. A third option, many worlds interpretation, keeps both locality and realism, but multiplies universes. Every measurement splits reality into branches, one for each possible outcome. In one branch, you measure spin up, in another, spin down. Both are real. The correlation between entangled particles isn't mysterious in this view. It's just that each branch contains a consistent pair of outcomes. But you never experience the split, so you can't test it directly. None of these interpretations is provably correct. They all reproduce the same experimental results. The disagreement isn't about what happens, but about what it means. And that's the uncomfortable part, because it suggests that quantum mechanics is complete as a predictive tool, but incomplete as an explanation. We can calculate probabilities with absurd precision, but we can't agree on what the math is describing. What we do know is this: entanglement is real, universal, and unavoidable. Every interaction creates it. Every collision, every photon absorbed, every quantum event leaves behind a web of correlations that never fully disappears. Most of the time, these correlations are too weak or too scrambled to detect. But they're there, linking particles that once touched, no matter how far apart they drift. And that raises a question physics doesn't like to ask. If everything that has ever interacted is still entangled in some residual way, what does that imply about the structure of space itself? Are we treating space as a container when it's actually a network of quantum connections? Is distance an emergent property, something that only appears to exist when you average over countless entangled degrees of freedom? Some theorists think so. In the ER equals EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, quantum entanglement might be equivalent to microscopic wormholes threading through space-time. Two entangled particles aren't connected across space. They're connected through space, via a geometric shortcut too small to traverse, but real nonetheless. If true, the fabric of space-time isn't fundamental. It's woven from entanglement itself. This is speculative, but it's taken seriously because it offers a way to reconcile quantum mechanics with general relativity. In this view, space isn't an arena where things happen. It's what entanglement looks like from the outside. Distance is a measure of how entangled two regions are. The closer they are, the more quantum information they share. But even if that's right, it doesn't resolve the tension. It just moves it. Because now the question becomes, if space is emergent, what is entanglement emerging from? What is the substrate? And how does measurement, a macroscopic, irreversible process, trigger the collapse of a shared quantum state that spans potentially infinite distance? Research by Professor Huan Yin's team in China suggests that whatever coordinates entangled particles operates at speeds at least 10,000 times faster than light. But that's misleading. There's no thing moving. The correlation is instantaneous because it's not causal, it's structural, built into the quantum state from the beginning. Measurement doesn't send a signal, it reveals a pre-existing relationship that has no classical counterpart. And perhaps the strangest part is that we use this every day without understanding it. Quantum cryptography relies on entanglement to detect eavesdropping. Quantum computers use it to process information in ways classical machines can't. We've turned a philosophical paradox into a technology, not by solving it, but by learning to work within its constraints. But that pragmatic success doesn't erase the conceptual problem. We're still left with a universe that permits correlations with no mediating cause across distances where causal contact is impossible. We're left with a choice between interpretations that all feel incomplete, and we're left with the suspicion that the question itself might be malformed, that we're asking what entanglement is when the universe might not operate according to categories that make sense to us. The real trouble isn't that entanglement seems impossible. It's that we've confirmed it works over and over in conditions where nothing classical could explain it. Top quarks, particles as massive as gold atoms, are produced in collider collisions and decay within 10 to the power of minus 24 seconds. They exist so briefly that even light can't cross the space between them before they're gone. Yet when physicists at the Large Hadron Collider measure their spins, they find perfect anti-correlation. The quarks know what the other is doing, despite never having time to communicate, even at light speed. This isn't a thought experiment, it's data from the Atlas detector in 2023, analysed with quantum tomography techniques borrowed from information theory. The statistical significance exceeds 5 sigma, meaning the odds of this being a fluke are less than 1 in several million. And it's not an isolated case. In 2017, China's Mishia satellite demonstrated entanglement over 1,203 kilometers between ground stations in different provinces. The photons violated Bell inequalities while separated by distances that made any subluminal signal exchange impossible. By 2025, the Jinan 1 microsatellite extended this to 12,900 kilometers, linking China and South Africa. The scale matters because it closes loopholes. Early Bell tests faced criticism. Maybe the detectors weren't fast enough, or maybe the particles were somehow pre-coordinated before separation. But when you entangle photons in orbit, send them to opposite sides of a continent and measure them within nanoseconds of each other, making the measurement events space-like separated, there's no room left for hidden communication. The correlations persist anyway. What's striking is how universal this phenomenon turns out to be. Entanglement isn't confined to carefully prepared laboratory states. It shows up everywhere quantum mechanics operates. Inside protons, quarks and gluons are entangled across distances smaller than 10 to the power of -15 meters, less than a quadrillionth of a meter. When physicists at Brookhaven National Laboratory analysed electron-proton collision data using entropy measures from quantum information theory, they found signatures of entanglement embedded in the debris patterns. The protons arrived already entangled internally, and that entanglement determined measurable properties of the collision products. Then there are the macroscopic cases. Researchers at Delft University etched silicon beams 10 micrometers long, roughly the size of a bacterium, and used laser pulses to entangle their vibrational states. The beams oscillated in superposition, sharing energy in a way that couldn't be assigned to one beam or the other until measurement. The entangled state lasted only milliseconds before environmental noise destroyed it, but the fact it existed at all pushes quantum behavior into a regime where objects are nearly visible to the naked eye. At the University of Basel, a team entangled hundreds of atoms in a Bose-Einstein condensate. The atoms collided constantly, their spins becoming correlated through interactions. When the researchers measured spin in two separate regions of the cloud, they observed the EPR paradox directly, perfect correlations that violated classical bounds. This wasn't two particles carefully isolated. It was a many-body system, messy and dynamic, and entanglement emerged naturally from the physics. So entanglement scales. It works at the smallest distances inside hadrons, across laboratory tables, between satellites and ground stations, and in macroscopic mechanical systems. It survives in top quarks that decay almost instantly and persists in atomic clouds cooled to near absolute zero. It shows up in high-energy collisions and low-temperature condensates. The experimental record makes one thing clear: this isn't a fragile anomaly. It's the default behavior of quantum systems. Which brings us back to the conceptual problem. How do particles separated by space, sometimes cosmological distances, maintain correlations that appear instantaneous? The standard answer is that nothing actually travels between them. The correlation was established when the particles interacted, and measurement simply reveals a pre-existing relationship encoded in the joint quantum state. But that answer, while technically correct, doesn't resolve the deeper tension. It shifts the question. Because if the correlation is pre-existing, what does that mean? In classical physics, pre-existing information lives in the particles themselves, hidden variables that determine outcomes in advance. Bell's theorem rules that out. The correlations are stronger than any local hidden variable theory can produce. So the information can't be stored locally. It has to be stored non-locally, in the relationship between the particles. But relationships aren't physical objects, they're abstractions. And if the fundamental structure of reality is relational rather than substantive, we're forced to rethink what physical means. This is where the ER equals EPR conjecture enters. Proposed by Juan Maldacena and Leonard Susskind, it suggests that quantum entanglement might be geometrically equivalent to Einstein-Rosen bridges, wormholes. Not traversable wormholes large enough to send signals through, but microscopic connections threading space-time at the Planck scale. In this picture, entangled particles aren't connected across space. They're connected through space via a geometric shortcut, too small and too unstable to exploit for communication, but real nonetheless. If true, space-time itself becomes an emergent structure woven from entanglement. Distance wouldn't be fundamental. It would be a measure of how much entanglement two regions share. The closer they are, the more quantum information links them. The farther apart, the less. Space would be what entanglement looks like from the outside when you average over countless microscopic connections. This isn't proven. It's a speculative framework trying to reconcile quantum mechanics with general relativity. But it's taken seriously because it offers a way out of the impasse. If space is emergent, then the question, how do particles communicate across space, dissolves. They don't. They're already connected at a level more fundamental than spatial separation. But even if this is right, it doesn't fully resolve the measurement problem, because measurement is a macroscopic, irreversible process that involves detectors, amplification, and ultimately human observers. And somehow this macroscopic intervention, this act of asking a question, forces the quantum state to collapse into a definite outcome. How does that work if the system spans light years? In the many worlds interpretation, it doesn't. There's no collapse. The measurement entangles the observer with the system, and different outcomes occur in different branches of the wave function. You measure spin up in one branch, spin down in another, and both branches are equally real. The correlation between distant particles is maintained across branches. They're always anti-correlated within any given branch, but no signal propagates. The branching happens locally at each measurement site. In the pilot wave interpretation, particles always have definite positions guided by a non-local wave function. The wave function evolves deterministically according to Schrödinger's equation, and particles follow trajectories determined by the wave. When you measure one particle, you're interacting with the wave, and that interaction instantaneously affects the guidance for the other particle. The non-locality is explicit here. It's built into the theory, but it doesn't violate relativity because the guiding wave can't be used to send information. You can't control the outcome of a measurement, so you can't encode a message. In relational quantum mechanics, properties only exist relative to interactions. There's no absolute state. When you measure a particle, you're not revealing a pre-existing fact, you're creating a fact relative to you. Another observer in a different location would create a different fact relative to them. The correlations between entangled particles are maintained because the relational structure is consistent across contexts. But there's no single objective reality underlying all observations. Each interpretation handles the non-locality differently, but none of them denies it. The correlations are real. They've been measured too many times, under too many conditions, to dismiss. What's in dispute is what they mean. What kind of reality could produce them? And this is where the philosophical discomfort becomes acute. Because we're used to thinking of objects as self-contained entities with intrinsic properties. A rock has mass whether you look at it or not. A star emits light whether anyone measures it or not. Properties belong to things, but entanglement suggests that some properties, perhaps the most fundamental ones, don't belong to individual objects. They belong to relationships. They're features of the correlation structure, not of the particles themselves. This dissolves the boundary between parts and wholes. An entangled system isn't a collection of independent pieces. It's a single, indivisible entity that happens to be spatially extended. You can't describe the state of particle A without reference to particle B. They don't have separate identities, and if this applies universally, if everything that has ever interacted remains entangled to some degree, then the universe isn't a collection of objects. It's a single, vast, interconnected web of quantum correlations that we carve into things for convenience. That's not mysticism. It's a direct consequence of taking quantum mechanics seriously. The formalism doesn't describe a world of discrete objects bouncing around in space. It describes a world of superpositions and correlations that only crystallize into definite outcomes when observed. And the fact that this mathematical structure predicts experimental results with absurd precision across every scale and energy regime tested suggests it's capturing something fundamental about how reality is organized. But here's what still doesn't sit right. If entanglement is universal, if it's woven into the fabric of space-time itself, then why does measurement collapse it? What's special about observation that breaks the symmetry? Why does asking a question force the universe to choose an answer when, left alone, it seems content to remain indefinite? Some argue there's nothing special about measurement. It's just another interaction, and what we call collapse is really decoherence, the quantum system getting entangled with a large environment that washes out interference effects. But decoherence explains why we don't see superpositions at the macroscopic level. It doesn't explain why we see definite outcomes at all. The wave function still contains all possibilities. It just becomes effectively classical because the phases are scrambled. Others argue consciousness plays a role, not in a mystical sense, but in the sense that observation requires an observer, and observers are macroscopic systems with irreversible dynamics. Maybe collapse happens at the interface between quantum and classical, wherever information becomes irreversible. But that just relocates the problem. Where exactly is that interface? And why should irreversibility matter? The truth is we don't know. Entanglement works. We can create it, measure it, exploit it for quantum cryptography and computation. But we can't explain why it stops working when we look at it. And that gap between the formalism that predicts correlations and the physical mechanism that produces them is where the real mystery lives. And that gap between the formalism that predicts correlations and the physical mechanism that produces them is where the real mystery lives. So let's shift perspective slightly. Stop thinking about measurement as something we do to the system. Think about measurement as something the system does to itself. In normal quantum mechanics, you have a system, say 2 entangled particles, and then an observer who comes along and measures one of them. The observer is external. The measurement is an intervention. But what if the observer is also a quantum system? What if the measurement apparatus is made of atoms that obey quantum rules? Then the whole picture changes. The particle doesn't collapse because you looked at it. It becomes entangled with the measuring device. And now you have a bigger entangled system, particle plus detector, still in superposition. If you then look at the detector, you become entangled too. And now the system includes you, your brain, your neurons, the electrical signals representing what you saw, all of it quantum, all of it entangled, all of it in superposition. So where does it end? When does the wave function actually collapse? This is called the quantum measurement problem, and it's been haunting physicists since the 1930s. The math says superposition should propagate indefinitely. Once you're entangled, you stay entangled. There's no special moment when reality snaps into focus, and yet, subjectively, you experience a definite outcome. You see spin up or spin down, never both. So either something breaks the chain, some physical process that forces a choice. Or the chain never breaks and all outcomes happen, just in different branches of reality. That's the many worlds interpretation. Every measurement splits the universe. In one branch, you see spin up. In another, you see spin down. Both versions of you exist, neither aware of the other. It sounds absurd, but it's mathematically consistent. It takes the equation seriously without adding collapse by hand, and it explains why entanglement seems to break when you look. It doesn't break. You just become entangled with the system, and from inside your branch, the other outcomes are invisible. But many worlds doesn't solve the measurement problem. It relocates it. The question becomes, what determines which branch I experience? If all outcomes happen, why do I perceive only one? Some say the answer is decoherence. When a quantum system interacts with a large environment, air molecules, stray photons, thermal noise, the different branches become effectively independent. They can no longer interfere with each other. And that's why the macroscopic world looks classical. Not because superposition disappears, but because the branches separate so thoroughly that they might as well not exist from each other's perspective. Decoherence explains why you don't see cats that are both alive and dead, but it doesn't explain why you see a live cat rather than a dead one. It doesn't explain the subjective fact of experience, why this branch, this outcome, this moment feels real. And this is where things get uncomfortable again. Because if entanglement is universal, if every interaction entangles systems, then the boundary between quantum and classical isn't sharp. It's arbitrary. We draw it wherever it's convenient. We say the particle is quantum, the detector is classical. But the detector is made of particles. We say your brain is classical, but your neurons fire through ion channels governed by quantum rules. So where exactly does the quantum world end and the classical world begin? Nowhere. The boundary is a useful fiction. Now think about what that means for entanglement. If there's no clean division between quantum and classical, then entanglement isn't something that happens only in carefully controlled labs. It's happening everywhere, all the time. Every interaction, every photon absorbed, every atom colliding creates entanglement. And once created, it never fully goes away. Decoherence hides it, but the correlations remain encoded in the environment. This is sometimes called the quantum web, the idea that the universe is a single, vast, entangled state, and every part of it carries information about every other part, however faintly. This isn't mysticism. It's a direct consequence of unitarity, the principle that quantum information is never destroyed. If you interact with something, you become entangled with it. And if entanglement is never truly erased, then the history of every interaction is preserved somewhere in the structure of correlations. The universe remembers, not in a conscious sense, but in the sense that its current state encodes its past. And if you could somehow reverse decoherence, unscramble the environment, you could in principle reconstruct what happened. That's why black hole information paradoxes are so troubling. If a black hole evaporates, where does the information go? If it's destroyed, quantum mechanics is violated. If it escapes, how? The answer probably involves entanglement. The information isn't stored in the outgoing radiation or the hole itself. It's stored in correlations between them. The entanglement structure encodes what fell in. But here's the deeper puzzle. If entanglement is the fundamental currency of reality, if correlations are more basic than objects, then why do we see objects at all? Why does the universe look like a collection of separate things rather than a single undifferentiated quantum state? Some argue it's because of decoherence. The environment carves the wave function into branches that don't talk to each other. Others argue it's because of symmetry breaking. The universe started in a symmetric state, and as it cooled, that symmetry shattered into distinct structures: particles, forces, space-time itself. But these explanations feel incomplete. They describe how objects emerge from quantum soup, but they don't explain why we perceive them as separate. Why does your experience have boundaries, a sense of here versus there, self versus world, if the underlying state is one seamless web? This question loops back to measurement, because measurement isn't just about getting information, it's about making distinctions. When you measure spin, you're asking, is it up or down? You're imposing a binary choice on a system that was neither. And the act of asking forces the system to answer. The universe doesn't naturally divide itself into discrete outcomes. We do that. Our brains, our instruments, our questions, they carve reality into pieces. And maybe that's the real role of the observer. Not to collapse the wave function, but to define what counts as a measurement in the first place. To decide which correlations matter. But if that's true, then the observer isn't passive. The observer is active. By choosing what to measure, you determine which aspects of reality become definite. And this is starting to sound uncomfortably subjective. It suggests that the world you experience depends on the questions you ask, not in a vague philosophical sense. In a precise, operational sense, if you measure position, you collapse momentum. If you measure spin along one axis, you erase information about spin along another. The act of observation isn't neutral. It shapes the reality it observes. Now combine this with entanglement. If measuring one particle affects its entangled partner, and if the choice of what to measure is up to the observer, then the observer's decision determines the state of both particles. And if entanglement extends throughout the universe, if everything is correlated with everything else, then the observer's choices ripple outward, not causally in the sense of sending signals, but structurally in the sense of defining which correlations become real. This is the participatory universe idea. The notion that reality isn't a pre-existing stage we observe from the outside. It's a process we participate in. By measuring, by choosing what to pay attention to, we help determine what exists. And this brings us back to the original question. What is entanglement, really? It can't just be a correlation, because correlations don't violate Bell inequalities. It can't just be faster than light influence, because no information travels. It can't be hidden variables, because experiments rule that out. So what's left? Maybe entanglement is evidence that reality isn't made of stuff, it's made of relationships. And relationships don't have locations. They don't travel through space. They're not properties of particles, they're properties of the network. The quantum state isn't a list of particle positions, it's a map of correlations. And when you measure one part of the network, you're asking about its relationship to another part. The answer you get depends on the structure of the whole. This dissolves the boundary between parts and wholes in a different way. It's not just that entangled particles form a single system, it's that particles themselves might not be fundamental. What's fundamental is the pattern of correlations. Particles are nodes in the network, and when we measure them, we're not discovering pre-existing properties, we're probing the network structure. The properties emerge from the relationships. They're not intrinsic, they're relational. And if that's right, then space itself might be emergent from entanglement. This is the ER equals EPR conjecture. The idea that entanglement and space-time geometry are two sides of the same coin. When two regions of space are entangled, they're connected, not through space but by space. The entanglement creates a geometric link, a kind of quantum wormhole, and space-time, at its most fundamental level, might just be the geometry of quantum correlations. Distance isn't primary, entanglement is primary. Distance is how much entanglement there isn't. This would explain why entanglement seems to ignore space. It's not ignoring space, it's creating it. And it would explain why general relativity and quantum mechanics are so hard to unify. They're not describing different things. They're describing the same thing from different perspectives. Relativity describes the geometry. Quantum mechanics describes the correlations. And the geometry is built from correlations. But this is still speculative, and it doesn't answer the hardest question. Why does reality have any structure at all? Why are there correlations rather than none? Why does the universe bother to be consistent? If entanglement is fundamental, what enforces it? What makes particles respect their correlations across arbitrary distances? There's no mechanism, no signal, no causal link, just the math, insisting that if you measure here, the result there is determined. And the math works. Every test confirms it, but the math doesn't explain itself. And the math doesn't explain itself. It predicts, it describes, but it doesn't say why. This is where physics hits a wall. Not a wall of ignorance, but a wall of interpretation. The equations are clear. The experiments are consistent, but what they mean at the level of fundamental reality remains open. Some physicists argue we should stop asking why. The math works, the predictions match, and maybe that's all we can reasonably expect. This view, sometimes called instrumentalism, treats theories as tools rather than truths. A hammer doesn't need to reveal the nature of carpentry, it just needs to drive nails. Similarly, quantum mechanics doesn't need to explain what entanglement is, only how to calculate it. But others can't let it go. They argue that science has always gone deeper than mere prediction. Newton's laws didn't just calculate orbits, they revealed that gravity was universal. Einstein didn't just fix Mercury's orbit, he showed that space-time itself curves. And quantum mechanics, despite its predictive success, still feels incomplete to many. Not because it's wrong, but because it describes reality in terms that seem fundamentally alien to existence itself. This tension runs through the entire debate about entanglement. On one side, the formalism. The math is elegant, powerful, and empirically bulletproof. On the other, the intuition. Our deep-seated sense that objects should have properties, that space should separate things, that causes should precede effects. And no amount of experimental confirmation can fully bridge that gap, because the gap isn't empirical, it's conceptual. You can measure entanglement, you can exploit it technologically. China's Messier satellite, launched in 2016, uses entangled photons to create quantum-encrypted communication channels across thousands of kilometers. In 2025, the Jinan-1 microsatellite established a quantum link stretching 12,900 kilometers between China and South Africa. These aren't philosophical abstractions, they're working systems. Entanglement is as real as any phenomenon in physics, but real doesn't mean understood. Consider what actually happens in these satellite experiments. Two photons are entangled at the source. One is sent to a ground station in one country, the other to a station thousands of kilometers away. When measured, their polarizations correlate perfectly, exactly as quantum mechanics predicts. No signal passes between them, no information travels, Yet the correlation persists. The technology works because the math works. But the math doesn't tell you what's happening between the measurements. It doesn't tell you whether the photons know about each other. It doesn't tell you whether the correlation is instantaneous or whether time even applies. It just says, measure one and you'll know the other. And that's the thing. We've gotten very good at using entanglement without understanding it. Quantum computing relies on it. Quantum cryptography depends on it. These technologies don't require anyone to solve the interpretation problem. They just require the equations to hold. And they do. But every time someone builds a quantum computer, every time someone sends encrypted data via entangled photons, they're exploiting a phenomenon that still lacks a satisfying explanation at the level of what exists. The technology is ahead of the metaphysics. This creates an odd situation. Entanglement is simultaneously the most experimentally verified and the most conceptually elusive feature of modern physics. We can produce it, measure it, control it, and scale it, but we still don't have consensus on what it is. One response is to embrace the mystery, to say that nature simply operates in ways that defy human intuition, and our job is to describe, not understand. This isn't defeatism, it's humility. The universe doesn't owe us an explanation in terms we find comfortable. Maybe entanglement is just one of those features of reality that can't be translated into everyday concepts without losing something essential. Another response is to keep pushing, to develop new interpretations, new mathematical frameworks, new experiments. The history of physics is full of moments where something seemingly mysterious became clear once the right conceptual shift occurred. Quantum mechanics itself was once considered hopelessly bizarre. Now it's the foundation of chemistry, electronics, and materials science. Maybe entanglement is just waiting for the next conceptual breakthrough. But there's a third possibility, one that's harder to accept. What if entanglement isn't mysterious because we haven't figured it out yet, but because it reveals something fundamental about the limits of what can be figured out? What if reality, at its deepest level, simply doesn't have the kind of structure we expect? This isn't mysticism. It's a serious possibility raised by the formalism itself. Quantum mechanics describes the world in terms of probability amplitudes, which combine in ways that don't correspond to any classical process. You can't visualize them. You can't build a mechanical model. They're mathematical objects that encode correlations, and those correlations don't reduce to anything more familiar. If that's right, then entanglement isn't a problem to be solved. It's a feature of how reality is put together, and our discomfort with it says more about our expectations than about the universe. But even if you accept that, questions remain. Why does reality have correlations at all? Why does measuring one particle determine the other? Why is the universe structured such that distant events can be linked without any causal connection? One answer comes from the idea that reality isn't built from objects, it's built from information. This perspective, associated with physicists like John Wheeler, suggests that what we call particles and fields are really patterns in an underlying informational structure. Entanglement, in this view, isn't a strange connection between distant objects. It's a reflection of the fact that the objects aren't really separate to begin with. Wheeler famously summarized this with the phrase, "it from bit," the idea that every physical thing ultimately derives from information. Not information in the sense of human knowledge, but in the sense of fundamental binary distinctions. Yes or no, spin up or spin down, here or there. And entanglement is what happens when these distinctions are correlated at the most basic level. This shifts the question. Instead of asking how particles communicate across space, You ask why the information structure of the universe includes these non-local correlations. And that's a different kind of question, one that might not have a mechanical answer. But it still doesn't explain why. Why information? Why correlations? Why anything at all? These questions push beyond physics into metaphysics. And that's where the real tension lies. Physics can describe entanglement perfectly, but it can't tell you why reality is the kind of thing that allows entanglement in the first place. That's not a failure of physics, it's a boundary condition. Science operates within reality, using the rules reality provides. It can't step outside and explain where those rules come from. This is where some physicists become uncomfortable, not because they think science is incomplete, but because the questions start sounding unfalsifiable. If you ask why the universe has quantum mechanics at all, there's no experiment that can answer that. You can only describe the universe we have, and in this universe, entanglement is woven into the fabric. Perhaps the most unsettling part is this. Entanglement doesn't just challenge our understanding of objects or space. It challenges the idea that understanding itself can be complete. Every explanation assumes something. Classical mechanics assumed objects had definite positions. Quantum mechanics doesn't. But quantum mechanics assumes probability amplitudes, Hilbert spaces, and unitary evolution. What if those assumptions are just as arbitrary? What if every theory we build is just another interface, another set of convenient fictions, and the real structure underneath is something we can never fully grasp? That's the truly uncomfortable possibility. Not that we haven't solved the mystery of entanglement yet, but that the mystery might be permanent. Not because we're not smart enough, but because the universe might not be the kind of thing that can be fully understood from within. And yet the work continues. Experiments push entanglement to new extremes. In 2023, physicists at the Large Hadron Collider measured entanglement between top quarks, the heaviest known particles, each as massive as an atom of gold. These quarks exist for less than a trillionth of a second before decaying. And even in that fleeting instant, their spins remain correlated across distances too large for light to cross in time. This means entanglement operates at the highest energies, the shortest lifetimes, and the most extreme conditions we can create. It's not fragile, it's fundamental, and the more we test it, the more solid it becomes. But solid doesn't mean explained. Entanglement survives every challenge we throw at it, and with each success, the mystery deepens. Not because the phenomenon is elusive, but because it reveals how little we actually understand about what it means for something to exist. So where does this leave us? Not with comfort, not with closure, but maybe with clarity about what kind of problem this actually is. Entanglement isn't mysterious because we don't understand it mathematically. We do. The equations work. They predict, they hold, they scale. From photons separated by continents to quarks living for less than a trillionth of a second, the correlations remain. The mystery isn't in the behaviour, it's in what the behaviour implies. And what it implies is that the universe is not made of objects in the way we assume. That's the uncomfortable part. Not that particles are connected, but that treating them as separate things in the first place might be the error. Entanglement doesn't break the rules. It reveals that the rules we thought we understood were always approximations. Good enough for daily life, good enough for engineering, but not accurate. The world you experience, objects with locations, things moving from here to there, causes preceding effects, is a high-level summary. It's what reality looks like when you ignore the correlations. But those correlations are always there, underneath, holding the structure together in ways that don't fit the story. And here's the deeper issue. We can't just update the story and move on, because every story we tell assumes something. It assumes time flows forward. It assumes space separates things. It assumes measurement reveals pre-existing facts. Entanglement challenges all three. Bell's theorem didn't just prove Einstein wrong, it proved that any theory trying to restore classical intuition will fail. Not because we haven't been clever enough, but because the structure of reality doesn't permit it. You can't fix this with better hidden variables. You can't fix it with better geometry. The problem isn't in the model, it's in the assumptions we bring to modelling. Some physicists have tried to sidestep this by treating entanglement as purely informational. They say it's not about particles communicating, it's about how information is distributed across a system. And that's technically correct, but it doesn't dissolve the mystery, it just relocates it. Now the question becomes, why does the universe organise information in this non-local way? What kind of structure permits correlations that ignore spatial separation? And that question doesn't have a mechanical answer. It's not a gap in our knowledge that another experiment will close. It's a boundary between what physics describes and what it presupposes. This is where some people get frustrated. They want physics to explain everything. Not just how things behave, but why those behaviours exist at all. But that's not what physics does. Physics operates within reality. It uses the rules reality provides to predict outcomes, but it can't step outside and justify those rules from a more fundamental layer. There is no more fundamental layer. The rules just are. And entanglement is one of those rules. It's not a force, it's not a signal, it's not a thing doing something to another thing. It's a structural feature of how the universe is organised at its base. And we only notice it because we're used to thinking in terms of objects and distances, categories that don't apply cleanly at the quantum level. So maybe the real lesson isn't that entanglement is strange, it's that our expectation of separateness was always wrong. We built an intuition around objects because that's what survival required. Track the prey, avoid the predator, navigate the landscape. None of that needs quantum mechanics. It just needs approximations that work at human scales. But approximations aren't truths, they're scaffolding. And entanglement is what you see when you dismantle the scaffolding and look at the structure underneath. The particles aren't violating separation. They were never separate in the way we imagined. The correlation isn't mysterious, it's primary. What's mysterious is why we ever thought independence was the default. And once you see it that way, the question shifts. You stop asking how particles stay connected and start asking why anything ever seems disconnected. Why does the universe present itself as a collection of distinct objects when the math says it's one continuous state? Decoherence offers part of the answer. When quantum systems interact with large environments, the interference terms vanish. The superposition is still there mathematically, but it becomes unobservable. The branches separate, and in each branch, things look classical. Objects have locations, measurements have outcomes. The world makes sense, but that's just hiding the weirdness, not resolving it. The full quantum state still contains all branches. The entanglement is still there, encoded in correlations too complex to track. You haven't eliminated non-locality, you've just made it invisible. And maybe that's the point. Maybe the universe doesn't care whether we understand it. It just has to be consistent. And consistency doesn't require objects. It doesn't require space as a fundamental container. It just requires correlations that hold across measurements. Entanglement provides those correlations. That's enough. But it's not enough for us. Because we're not just calculating probabilities, we're experiencing outcomes. And experience has a structure. It has a subject and an object. A here and a there, a before and an after. Entanglement undermines all of that. It says the structure of experience isn't the structure of reality, and that's where the discomfort becomes permanent. Not because entanglement is paradoxical, but because it's not. The math is clean. The experiments are clear. The phenomenon is robust. The paradox is in us, in the gap between how reality operates and how we need to think about it to function. We can't navigate the world by thinking in terms of quantum states and non-local correlations. We need objects, we need separation, we need causes and effects arranged in time. Those categories are biologically necessary, but they're not metaphysically accurate. And physics can't resolve that tension. It can only map it. It can show you where the approximations break down. It can prove that locality fails, that realism fails, that the classical picture is incomplete. But it can't give you a new picture that feels as solid as the old one, because the old one was never solid, it was just useful. So entanglement remains, not as a problem waiting for a solution, but as a permanent feature of reality that refuses to fit the framework we bring to it. And maybe the real mystery isn't the phenomenon itself, it's why we keep expecting the universe to make sense in human terms. Because it doesn't owe us that. It doesn't owe us objects or locations or causes. It just has to be consistent with itself. And it is. We're the ones struggling to keep up.